This is my talk. It is clear that these results are joint with Yuri Kharkov, my co-author, but it is not clear what is my talk about, probably. First, I want to note that also there is a word harmonic in contrast to two previous lectures and to many yesterday lectures. It is not about harmonic functions, not about. And what is this about? What area? Okay. What area? Area is the Walsh analysis. And what is it, Walsh analysis? Walsh analysis is a new enough topic of analysis, appeared in the middle of the 20th century. There are two known monographs. First one is due to Hungarians, authors Ship, Waite, and Simon. And the second one, well-known Russian authors, Golubov, Yefimov, Skvortsov. Both on Walsh series, and here we see harmonic analysis. What is this? What is this about? It is about harmonic analysis different from classical harmonic analysis. And also you see dyadic. Really first, both monographs deal with dyadic situation, but today it is not necessary dyadic. So what is this classical Walsh analysis, or it may be called dyadic analysis? It is studied in two different forms. The first one on the Cantor group. What is it, Cantor group? Cantor group, elements of the Cantor group are sequences. Each element of the sequence either 1 or 0. So this is really dyadic group. And addition, coordinate-wise addition, modular 2. This is Cantor group. Says firstly it was studied. This is groups, hence there are characters on the group, and there is Fourier transform. If there is Fourier transform, then there exists Fourier analysis. But another one development on this is positive half-line. Positive half-line. My co-author studied harmonic analysis on the positive half-line, Kratasov and his students. So this was developed, but positive half-line, it is very close to the Cantor group. What is positive half-line? Each point can be written in dyadic system, ones and zeros. But there is a difference. There is a difference. It is not a group. Nevertheless, they introduce coordinate-wise addition, and also this is not a group. The same formulas as here for characters is used for for half line, and this is studied. This is studied. Oh, I said this already. Analogs of characters appear, correspond to exactly the same formulas. Dyadic not necessary. Instead of the Cantor group, it is possible to consider the Vilenkin group. This is not associated with number 2 with arbitrary positive number. Why we are interested in Walsh analysis? Why? because of the following feature, interesting feature. In contrast to real setting, there exist compactly supported band-limited functions, which are called test functions. This never happens in usual harmonic analysis, either compactly supported or band-limited. Band-limited means that the Fourier transform is compactly supported. In many problems, we want to deal with good functions. What is a good function? Decay is good, the faster decay is better, and we want to deal with smooth functions. What is a smooth function? This means the decay of the Fourier transform is good. And what is the best in in classical analysis? Schwarz classes, but we are interested in wavelets. In wavelets, it is very important to deal with compactly supported functions. So it's impossible to have compactly supported function itself and its Fourier transform. And here, such function exists. So this function of special interest. And examples for half-line was studied already. Such examples exist. And my co-author Yuri Farkov, together with his students, organized applied area signal processing. I said we are interested in wavelets, and wavelets appear in connection with signal processing, with applications. It is very important. And they compared standard wavelet system, Tobish systems, which was developed about 30 years ago, with these functions on with this wavelet system defined on half-line in that harmonic analysis. And it appears that they are better for fractal signals really needed. So we really needed to deal with this exotic harmonic analysis because not only because of theoretical, but also because of applied applications. What is this paper about? We study multi-resolution analogs of half-line. Half-line is one-dimensional, and I'm going to define multi-dimensional half-line. First of all, we need digest. What is digest? And I remind title M positive vector. Half-line is positive, numbers one-dimensional vectors, and here we deal with vectors in Euclidean space of the d-dimensional Euclidean space, and M is a matrix. It is integer matrix such that all its eigenvalues is bigger than 1 in absolute value. Such such matrices are used in wavelet theory, and they are called dilation matrix. Such a matrix is called dilation matrix. The class of dilations or dilation matrices is calligraphic MD. If M is a dilation matrix, its determinant is bigger or equal than 2. It is integer. This is denoted by small m. So capital M is matrix, and this is absolute value of its determinant. Next, we introduce set of digits associated with M. We said that we introduce congruent modular M. We said that two integer vectors is congruent modular m, and write like this: if difference L minus k is equal to ms for some integer s. It's clear that this congruous relation, so the whole lattice ZD is splitted into cosets with respect to this congruence. And what is D? D is the set of digits if it consists of one representative of each coset. The first, it is known that the number of cosets is exactly m, small m, determinant. The first one is identical 0, and other representatives of the cosets. Representatives of the cosets. We also will deal with M star, the matrix transpose to M, and for this matrix it is also matrix dilation, and so the determinant is the same, the number of digits is also the same. This is notation for digits of this matrix, D star. Next, M reminds that M, all eigenvalues of M is strictly bigger than 1 modular, and hence M under the power minus 1, all eigenvalues of this matrix is strictly less than 1, and hence spectral radius is less than 1. And it is known that in this case, this relation holds for any delta such a series converges, and in particular for delta is equals 1. This is true. Hence, any x any series like this converges, and we denote by x plus the set of vector represented in this form. And next, x0 denotes the set of vectors such that this sum is finite. Finite have finite representation. And I note we will choose finite representation if only it exists. If exists finite, we choose finite and consider that this is a unique representation, and maybe in other situation, only infinite representation. Proposition 1. For every x from x0, there exists a unique finite representation. This is a simple statement. And another proposition, representation star, is unique for almost all x in x plus. So let us compare with half-line. More or less the same, but not exactly the same. First of all, if we consider if for any x which have a finite representation, we use it and consider that this is its unique representation. Then for half-line, we can say that not for almost all, for all unique representation. If there is finite, we choose it. If otherwise, it is unique. For example, the decimal system, either it is finite representation, there is, or periodic 9, But situation a little bit different.
Almost all.
almost all x from here. There exist not for all. I just going to explain that there exist, in contrast to half line, here there exist x which have two different infinite representation. That's why almost all. Just in this list, I will explain this. There, about 15 years ago, there was a paper of Petersburg mathematician Maximenko-Rabkin. In English translation, it was called expansion of vectors in powers over matrix. In Russian, it was called многомерная система счисления. I would prefer say in English, but it's a very strange thing. It looks that no translation of система счисления to English. Google Translate doesn't translate система счисления from Russian to English. But if I translate from English to Russian number system or numeral system, it translates система счисления. So I do not understand. Probably they also did not understand how to write, but more convenient to, because we understand very well Russian speaking, what is it система счисления, what is it многомерная система. Actually, they studied only integer vectors and their decompositions, and they introduced the term M9s. More or less clear. We have periodic 9 in the semi-line, and if this is not decimal, for example, in dyadic case, 9 is 1, and for every 9 is the same role of 9 plays m minus 1. And they investigated what happens with matrices. It appeared for some matrices, no analog of periodic 9. For some matrices, there exist several periodic 9, and not necessarily from one digits. For example, 1 to 3, 1 to 3, 1 to 3, and up to infinity. And they proved that, no, later, what they proved, let us consider this matrix. These are digits. 0 digit and non-zero, 2 digits, because determinant is 2. Next, it is easy to see that m squared s is digit, is equal to 1. It can be decomposed like this, and these are exactly positive, even degrees of m under the power minus 1 of s. Hence, next, let us consider arbitrary sequence. Yk is a digit, and let z be m squared s plus this sum. Because of this equality, we can rewrite like this. Here only even degrees, and here odd. So we have two different representations. But if this is finite, or there exists here a periodic 9, M9, then we have no two different. If there is periodic 9, we choose finite representation. But we are interested in two different infinities. But how many Y, how many such sequences? Continuum. Yes, and how many, Maximenko and Rabkin proved that the sequence, if Z, look to this representation, if Z has a finite representation, it may happen only if this sequence is finite, or it contains a sequence of M9s. But clearly that only countable set of such y, such y. So there exist y for which these are two different infinite representations. Okay, it's time to start my topic. Now I am ready to introduce the space of M positive vectors associated with matrix M. X is X plus minus the set of elements which have two infinite representation deleted of them. So the elements which have a finite representation, and we consider that it's only or unique, it's unique representation. So we have space X. This is just space of M positive vector. We have unique representation. Next, U, the number of elements of X such that Xj is equal to 0 for all negative, so for all j less or equal than 1. And let us return to the half line. This is unit interval 0, 1, and H is a set of X such that this is 0 whenever j is bigger than 0, and it's clear that this is an alloc of positive numbers. This is unit interval on the half line, and this is set of positive numbers. Of course, the same for X star. And you see half lines, very beautiful, very beautiful. This is quincunx matrix called, and the picture depends on choice of digits. This the same matrix, and we can choose digits 0, 0, 1, 0, small dragon, and if we choose such digits, then bigger. For M star, this is blue dragon. There are some other fractal sets. The one is called bear, and it's complicated for me to organize pictures. Okay. Next, very simple property of this set U. Mu is equal to such a union. So U is self-similar set. This is trivial because we take from U, this is the series of degrees started with negative degrees, -1, -2, etc. After multiplying by M, we have each element start with a digit. So this is such a union. Such self-similar sets are called attracted, and they were studied by many authors. And what is known? Non-trivial facts. After a set of zero measure, U is a compact set, has an empty interior, and the Lebesgue measure of U is also an integer number. If this is 1, it is such sets are called tiles. Protasov and his students recently actually studied these tiles, geometric property, and so on, especially for the matrices with determinant 2. Okay. Next, let us write our elements of the space X in this form as we write numbers. Integer part, comma, then fractional part is if X from U, we write this, 0, comma, that fractional part is if zeros from some number, we write as a finite fraction. Next, integers. Integers, it's more or less clear that analog of integers, integer vectors in our space, more or less the same as integers. But really, we can organize one-to-one correspondings. Let a number k, positive number k, may be represented. This is small m, determinant of matrix. Can be, of course, we write infinity, but of course this is finite sum, and the corresponding vector, integer vector, the same kj. This is one-to-one correspondence. So now we can numerate elements of the space H, integer vectors by usual integer numbers. H looks like this, and very important these sets. If n is equal to 0, this is u plus integer. So the whole half line is splitted by unit intervals. If m is positive, that these are smaller intervals. Why this is important? We will define class of functions which are constant on these step functions, so called. Next, we introduce addition. Addition is coordinate-based addition. These are digits, j, yj, and this is addition modulo m on d. Proposition 3, if x and y in x, then the sum is also in x. Of course, the same for x star. And so it is very similar to Vilenkin groups. Vilenkin groups not with matrix. The Vilenkin groups is one dimension, corresponds to one-dimensional case. Okay, but nevertheless, we will use formulas with matrix here. In Vilenkin group, this is number, and we will call. Of course, our space is not group. No associativity. We introduce adding, but no associativity. Nevertheless, usual the property of characters are satisfied. Okay. Next, probably I will miss this. Nobody knows what is Vilenkin. Christensen does not matter. Something what is true for Vilenkin groups is true here. Next, we introduce Walsh system, where the function alpha defined by the formula. So in the case of group, this is just characters with integer numbers, and this is definition of, so Walsh systems, Walsh functions appear. Walsh function theorem, Walsh functions is H periodic. It is clear what is H periodicity, plus H is equal to, doesn't change. And moreover, it is constant on these steps, on this step function. Walsh system is an orthogonal basis of the space L2 on U. So this is analog of harmonics. Walsh function is analog of harmonics. Okay, next, this linear combination of Walsh functions are Walsh polynomials, and this is an analog of the trigonometric polynomials. Characterization of Walsh. Next, we see we introduce Fourier transform following groups. This is not character, but similar to character. So this is Fourier transform. First, of course, on this is for summable function, and then for and this you can recognize here Plancherel equality, but with coefficients. Next, this is also similar to usual property, is usual Fourier transform and usual plus. We have the same. Okay. Next, I promise to introduce good functions, step function constant on these sets as n and compactly supported. And why this is a good function? No, because of this theorem. If f is L2 and this is step function, for f belong to this function to be step function, it is necessary and sufficient Fourier transform of f is compactly supported. So we have what I promised. We have a space f in this space, Fourier transform, the size of step and the size of Fourier transform, and Fourier transform is the same. So what I promised there exists, and they may be useful for. Thank you.